Okay, so linear maps. What even are linear maps? I don't know, but we're going to figure it out today. So a linear map is a function from one vector space to another. We're calling our vector spaces V and W, but you can call them whatever you want. And it's a linear map if the function satisfies these properties. So the first one you see on the top, we have phi of V plus W equals phi of V plus phi of W. And we got for all V and W in V. And the second property is phi of lambda V or phi of lambda W, whatever you want, equals lambda phi of V. So it doesn't matter if lambda's in the bracket or outside the bracket, basically. And sometimes you'll see it expressed, you'll combine these two and you'll just express this as phi of lambda V plus mu W equals lambda phi V plus mu of phi W. Okay, so sometimes you'll see them, I hope you can see that what we've done here is we've just combined the properties into one. But if you want to be really fancy, sometimes you'll see it expressed like this, phi of, and then we're going to put inside the bracket here a little sum, and we're going to put lambda I Vi from I equals 1 to n. That just means we're basically writing what we've done here, but for a general number of terms. So let's say we got n of them. So here lambda 1 is lambda 2 is going to be mu. This just represents like they're going to change every time, but we're doing the same thing. And that equals the sum of lambda I phi Vi from I equals 1 to n. So yeah, it's the same as above. We've done the same thing, just for n, lots of them. So I hope you can see that they're the same. Okay, so let's look at an example, okay? So we've got a linear map. Well, actually it's not linear. We're gonna find out if it's linear. We've got a function from f to 2 to f to 2. And I've given the rules of the function. Basically, you got a vector, x, y, and it's going to send it to x plus 1, y plus 1. So pretty simple. So we're going to look at a few instances of what this does, and then we'll get an idea of what's going on. So we're going to define v as 1, 1 and w as 2, 2. And so phi of v plus w, I've written out the steps there. Obviously v plus w is going to give us 3, 3 because we just added them together. And then we're going to apply phi to that, add 1 to the x and the y, and we're going to get 4, 4. Sorry, this shouldn't be here. Hold on. There you go. So if it's linear, that's going to be the same as phi of v plus phi of w. So phi of v is 1 plus 1 on top and 1 plus 1 on the bottom. And then phi of w is 2 plus 1 on top, 2 plus 1 on the bottom. And adding those up, you're going to get 2, 2 plus 3, 3, which gives us 5, 5. So we can see that these two are not the same, these guys here. So by our definition of linear maps, this function is not linear, okay? But I've gone a step further. We're going to see if it works with scalars too. So I've picked for our lambda 5. So 5 times lambda v, 5 times phi v, okay? So phi v is just 2, 2, okay? Because we've added 1 on top and 1 on bottom. So we've got our original v, which is 1, 1, added 1 to both, you get 2, 2. Times it by 5 is 10, 10. And if it's linear, that should equal phi of 5 times v. And so we know 5 times v is going to be 5, 5. And then we apply phi to that, we're going to add 1 to top and bottom, we're going to get 6, 6. So we see that in both cases, we've kind of double proved that this function is not a linear map. Okay, so we got another function here. I've changed the symbol this time. I realized I was saying the wrong Greek letter before. So this is phi, and it's going to take x, y, and it's going to send it to x plus y. So we've got v and w defined there. So let's see if it's a linear map. So phi of v plus w is going to be phi of, just adding them component-wise, v1 plus w1 on top, v2 plus w2 on the bottom. And by definition of our function, that is going to equal v1 plus w1 plus v2 plus w2. Sorry, my v's look like w's. And so if that's a linear map, that should equal the line below, which is phi of v plus phi of w. And so phi of v is v1 plus v2. Phi of w is w1 plus w2. You add them together, you're going to get exactly what you got on the top, just in a different order, but that doesn't matter. So we proved in this case, so step one is done. Let's see if it works for scalars. So phi of lambda v, sorry, it's wonky, I apologize. So phi of lambda v is going to equal, so we apply first lambda to v, we're going to get lambda v1 on top and lambda v2 on the bottom. And then we apply phi to that, we're going to get lambda v1 plus lambda v2. Okay, and then by the distributive property, we can take the lambda out, we can factor it out. Since lambda is not going to be 0, we're going to get lambda times v1 plus v2, sorry. And we know that that equals lambda times phi of v. Okay, because phi of v is v1 plus v1 plus v2. So that property is also satisfied. So not a super rigorous proof, but we've shown that this function is a linear map. Okay, one last example. This time it's going to be a bit different. We're defining our function as d, and we're doing that because it's going to be the differential function. I don't know if that's right. The function that basically differentiates what we give it. So we're defining v, our first vector space, as polynomials of degree less than or equal to 5, and w, polynomials of degree less than or equal to 4. And so we just define what the function does there. Not too important. Basically, that just means that we're differentiating it. So we know that this is a linear map because of the properties of what differentiation does, basically. We're not going to prove that rigorously here, but we know that d of p plus q is going to equal d of p plus d of q. And I've got a little example there. So let's say p is x and q is x squared. Obviously, if you ask to differentiate that, that's just going to be 1 plus 2x. That's just a property of the function. Again, you can prove that rigorously, but we're not going to do that here. And it's the same with lambda. D of lambda p is going to equal lambda d of p. And then we got, as an example, d of 5x is equal to, well, obviously that's 5, which is 5 times 1. So we see that this is a linear map.